This is Unit 6, Video 3. In this video, we will talk about the 4 gas laws. And these gas laws will be relating to us the 4 variables of gases that we've been talking about: temperature, pressure, volume, and moles. Moles, remember, is represented by the letter N, not the letter M, since M is used for mass. There are 4 of these laws. We'll describe each and then give you an equation for each. So the first one is Avogadros Law, named after the beloved Mr. Avogadro, who came up with the idea of moles. And so this law will relate moles. Now it will relate volume to moles. So the law says that the volume of a gas is directly proportional to the number of moles of gas. So it essentially says that the volume and moles of a gas are directly related. What this means essentially is as moles increases, volume increases in a direct way. So if you double the moles, then you will double the volume. Or if you divide the moles by 2, if you half the moles, then you half the volume. If you multiply by any number, volume goes up by the same ratio or proportion. Now this is assuming that T and P are held constant. You'll see that will relate 2 variables of the 4, and then the other 2 remaining ones will have to remain constant. So otherwise, temperature and pressure will also affect the volume. That's kind of the idea. Now the equation for this is K equals N over V. K is considered a constant, so you'll always see a constant in these equations. And then you would divide the 2 variables. This is actually how we show a direct relationship. We show it by saying that the 2 numbers divided by each other give you a constant. You can actually come up with some numbers to just prove this. If this were a 20, we'll say I have 20 moles and this was a 2, just picking up numbers. So 20 divided by 2 gives me a 10. So this would be a 10. If I increase the 20 up to 40, well, I've got to increase the 2 up to a 4, so that way 40 divided by 4 is still 10, and that's the idea. The same thing if you were to decrease the 20 down to 10, you'd have to decrease the 2 down to a 1. You'd have to divide by 2. And so this equation shows you the direct relationship of any 2 variables. In math, this is how a direct relationship can be represented, simply by dividing the 2 variables. You could have flipped these as well. It would have given you the same thing. You could say that K is V over N. The K would change, but it gave you the same idea. So this is Avogadro's law. Charles' law. Here's Mr. Charles. Now Charles is his last name, but he related the volume of a gas to its temperature. And he said that the volume of a gas is also directly proportional to the temperature. And this is assuming that the other 2 variables now, which is moles and pressure, are held constant. So in this case, we say as temperature increases, volume increases. So the same thing. If you triple the temperature, then you would triple the volume. Now here it says the absolute temperature. And for absolute temperature, remember there's only one absolute scale, and that is the Kelvin scale. So it'll be very important to be able to use Kelvin and not any other temperature scale for these calculations. So you have to be in the absolute idea. So the equation is the same as before, except now you have volume over temperature. So this is how we show the direct relationship of volume and temperature. Now, in fact, this is the principle on which hot air balloons are able to fly. Now, way back in the day, early in the 1700s, 1800s, people were actually flying before airplanes came along in these big hot air balloons. And the gas law that allowed them to do it was Charles' law. Mr. Charles himself was an avid participant in this kind of early aviation sport. Now, what happens here is, as anytime you've seen one of these hot air balloons try to get lifted into the air and really blown up, what they do is there's a flame that gets started that heats up the gas inside the hot air balloon. As the temperature increases, the volume of the gas increases. The air expands essentially. Now essentially it rushes out of the balloon, creating a smaller density of air inside compared to the density of the air outside. So essentially you have a huge balloon that has a smaller density, and that's why it's able to float. So it's really an idea of density, and that density is reduced by heating, because heating increases the volume. If the volume increases, then the density decreases. And that's really how it works. But it is due to Charles' law. can actually graph a law that's directly proportional. So here again is the equation. We said this is directly proportional because if volume goes up, temperature must go up to keep the K a constant. If you rearrange the equation by simply moving temperature to the left side, if you just multiply the temperature out here, what you get is V equals K times T. This is another way of seeing a direct relationship. The two variables are on opposite sides with the K with the constant being multiplied by one of them. And the way to see this graphed out is this is a Y equals mx graph. This is the most standard graph from algebra that you could look at. Y equals mx. And the way to graph this, m is usually a constant that is the slope of the line. So this, defines the steepness of the line. If the m is a low number, then the line isn't as steep as if m were a large number. So what happens here is if you graph this, you'll actually get a straight line just like this. Now this is an actual graph of the volume of a gas related to its temperature, or rather a volume as a function of temperature. So what they've done, these points, data points, are actually the volumes and at certain temperatures of a gas. Obviously we can see it form a straight line, and if you put a straight line to this, now this is measured under roughly moderate conditions, so around maybe 0 Celsius, up to maybe 200 Celsius and maybe down to negative 100 Celsius. And if you extrapolate this, if you allow yourself to extend the line all the way down, what you realize here as the temperature, so just back up a second, this line is a straight line because as temperature increases, volume increases. So we go from this point to this point in a direct relationship. Now, so you can backtrack this and realize that, well, the lower the temperature, the lower the volume. There'll come a point where volume becomes 0. You can't be negative volume. So at that point, temperature is at its absolute minimum, the lowest possible that it could be. And this is a very important graph historically because it was able to tell us absolute 0 long before we can actually reach it. We could reach it. So scientists actually figured out that absolute 0 was negative 273, the coldest possible temperature, way before we had instruments or techniques to reach a temperature this low. So this is actually a very important principle, and you can repeat this experiment and verify absolute 0 today in the laboratory. And that's the idea of Charles' law graph. All right, let's move on to Gay-Lussac's law, sometimes called the GL law. Here's Mr. Well, this is actually named after two gentlemen, Mr. Gay and Mr. Lussac. So this is one of them, which I cannot tell, but we'll find out. And this law says that the pressure, it relates the pressure of a gas to its temperature. And it says they are also directly proportional. So far we've seen every one of these laws relates these variables in a direct way. So assuming that the other two variables, as usual, are held constant, moles and volume. So as pressure increases, temperature increases by the same amount. And here is the same idea in terms of the equation. You divide the two variables to give you a constant. Now, where this is used in the modern times and not so modern times are in air conditioning units. So Mr. Gay-Lussac's law was instrumental in allowing us to enjoy summers in a comfortable way. So some say, that which is a more important invention than the hot air balloon, but that can be debated. And the way this works is the way we cool the temperature inside of the house is we first there's a special liquid in here, actually a gas that can become a liquid. So essentially they take a gas inside of here and they compress it. They increase the pressure. As the pressure increases of the gas, the temperature increases of the gas. And then what they do is they take it at high pressure, high temperature, and funnel it inside the house and suddenly drop the pressure. As the pressure drops, the temperature drops, and then you create a very cool gas, and then you allow it to blow into the house and cool the house. This is usually set up, an air conditioning unit is set up outside the house. That way it could release hot air to the outside and cool air to the inside. So air conditioning, thank you, Mr. Gay, Mr. Lussac, for the law. The last law then is Boyle's law. Now this is going to be the only law that's different from the other three. Mr. Robert Boyle is his name, related the volume of a gas to its pressure. And this will be inversely related. So inversely related means if one goes up, the other goes down. And that's exactly what this says. As pressure increases, volume decreases. Now again, this is by an exact amount. So if you double the pressure, you would divide the volume by 2. If you 1/3 the pressure, you increase the volume by 3, is how it works. Now, again, this is assuming that the other two variables are held constant. Moles and temperature remain constant. In other words, you're not adding any more gas to the system. All right, the equation here then is a little different than what we've seen. In this case, you've got the two variables multiplied by each other to give you a constant. Now, this would work the same way if we analyze it. The same idea works. Say if this were a 5 and this were a 2. Well, 5 times 2 gives us a 10, as before. All right, if I increase the pressure up to a 10, I double the pressure, I've got to reduce the volume down to a 1, and then 10 times 1 still gives me 10. I can do the same thing. I can reduce the pressure down to 2.5 just by dividing by 2. Then I got to multiply this by 2 up to 4. 2.5 times 4 is 10. That's the idea. This is the way we show an indirectly proportional equation, is the idea. Now here's Mr. Robert Boyle. He was actually very famous in the circle of chemists and scientists. He's a famous early scientist. And he created this little J tube that I'll talk about, I think, a little later. And this is a tube to measure pressure, a pressure of a gas. And you can also measure the volume of a gas. So I'll tell you about this J tube that he came up with just a bit later. Now, if you graph an inversely related equation, what you'll get is a curve. And in this case, the way to see it is the direct relationship we said was a straight line, but most people think, well, then an indirect relationship should be a straight line, maybe with a negative slope or something. But no, it's actually a curve. And the way this works, if we make this into a y equals x type of graph, this will be y equals 1/2. Rather, not 1/2, 1 over x. That's right. Y equals 1 over x. And if you've ever graphed y equals 1 over x, it'll give you this curve. Now, the way we get this is because the original equation, which was k equals p times v, if you rearrange it to say solve for v, you would divide the k down here, you get k divided by p, or, in other words, 1 over p, with some proportionality constant in front. And so you get y equals 1 over x graph, which gives you this curve. Now, this proportionality of k could be determined, and a fancy way of determining that in math is you actually invert your pressure unit, and which results essentially in a regular y equals mx type of graph. So essentially, this used to be 1 over p, so you've inverted it, and you've got yourself this inverse graph that then becomes a straight line. If you've seen this done before in math, then you understand. If not, don't worry too much, but essentially you invert every one of your x points, you 1 over that, and then you graph it, and then you get yourself this straight line. And then from this, you can actually get k, which is the slope. The k is always the slope of the line, which is, remember, rise over run, right? Slope is rise over run, which means if I can measure this distance and this distance, I can actually determine my slope, which means I can determine my k, which means I got a constant to my equation. So this is one of the ways that scientists determine constants and equations. All right, so that wraps up for us. Oh, one last little note about the J tube that I said Mr. Robert Boyle used. Actually, Mr. Robert Boyle had this tube purportedly outside of his house, so that way his visitors can always see and appreciate his law, which was relating pressure to volume. So the way it worked is, first of all, he filled it with mercury. So everybody had some mercury to play with back in the day. And the two lines would line up, which means the pressure in here is actually the same as the pressure out here, because the atmospheric pressure is what's pressing down this tube. So the pressure in here must be the same, because these levels are the same. What happened then is he can put little marks on it to show you that this is 60 milliliters of a gas. And then he can show his participants or viewers that you can double the pressure by just filling it with another 760 millimeters of mercury. We know that this is 760 millimeters of mercury because atmospheric pressure is 760 mg. And so he would fill it with another 760 millimeters of mercury. And lo and behold, the volume becomes 30, exactly halves. You double the pressure, you exactly half the volume. And his participants and viewers were very much overjoyed with such a precisely inverse law. That's the idea. And today you can actually use what's called a manometer. A manometer essentially is a vessel that measures pressure, or a contraption, a device that measures pressure. And so in this case, for example, if it's open to the atmosphere, we know that there's 760 coming in here. So then the height difference means that the gas has a pressure that's greater by this height difference to 760. So if this height difference maybe is, I don't know, 120, then we know the gas pressure is 760 plus 120, which is 880 millimeters of mercury. So you can actually measure pressure this way using a manometer. All right, so this should wrap up for us the third video, and we'll come on to calculations in the next video.